limit states design, what is that? What is limit states design? It's an engineering methodology, structural engineering that was adopted by the Building Code in 1995. It's a methodology or a way of designing that's existed for quite a long time, particularly in steel and concrete industries, and finally adopted by the National Building Code 95. So this is something that the U.S. doesn't have or haven't adopted yet for the wood frame. Therefore, that's a big driver as to why our span charts in Canada are much different than those in the U.S. Okay. So the method it's a more modern definition here, more modern, more rational approach, which basically takes statistical values or adds more weight or importance to the variability of things. So adds kind of, if you will, safety factor, okay, to things that are more variable than others. Okay. An LSD can be, or is broken down into two different parts, or two different things that needs to be calculated. What we call ultimate limit states and serviceability limit states. Okay. Ultimate limit states basically refers to the maximum, the limit basically for prior to collapse. Okay, so things like the bending, shear, compressive strength, all of those elements, all of those design properties lend themselves to the ultimate failure or not of the structure. Okay, so it's you want to make sure the bridge doesn't fall down. It doesn't matter how much it sways as long as it doesn't collapse. Okay, so that's the measurement of ultimate. Okay, so there are some design properties that we design to ultimate limit states, like bending, shear, and things like that. And on the flip side, the serviceability limit states is part of the equation, if you will, that lends itself more to the floor performance or to the performance of the structure. So again, a limit on how much the bridge will sway versus how much the bridge will, how much load does it take for the bridge to collapse. Okay? So there'd be a higher safety factor added to the ultimate limit because we want to make sure that doesn't, that never occurs. Whereas the performance side isn't quite as critical. Okay? So there's a big fancy long formula that looks real daunting and everything. Okay? And that would be, that's the LSD formula that would apply to all structures, bridges, concrete, and all that kind of stuff. But how does that actually work out to wood structures, in the case particularly in residential construction? A lot of these values in there are combinations of loads, wind, seismic, and all that kind of stuff. So when we actually break it down, and the multiplier in the front are factors of one kind of load, so there's multipliers as to how that all gets mapped out. Basically, to make a long story short, it can be dumbed down quite a bit because a lot of the factors in wood here would be a factor of 1. So if we start weeding out all those that don't apply, the formula gets simplified to 1.5 times the live load, and you add 50% to the live load, you add 25% to the dead load. And that would be the safety factor for the ultimate, for the first part, the ultimate limit states. Okay? So some design properties, when we size up a beam or a joist, some of the values get factored in order for the safety. We want to make sure that everything meets requirements for that. And other parts, such as deflection, for example, we don't need to factor those because the safety, the risk isn't as high, the probability of failure or catastrophe isn't there. So they get multiplied by a factor of 1. So again, when we look at deflection and things like that, we don't need to factor our numbers, whereas in certain items we do. Okay? So we'll see how that actually translates into load development. Any questions on that? Okay, so in summary, for gravity loads on most structures, the equation simplifies simplify it down to multiplying the live load by 1.5 and multiplying the dead load by 1.25. Okay. Again, higher safety factor on live load because the variability is much higher, whereas it's a lot more predictable as to what the dead load will be, so less of a safety factor. Okay. So, how does that actually look like when we map it out? So we have a typical live load of 40 pounds per square foot on a house, dead load of 10, we multiply that, so your factor live and dead load would be 60 and 12.5, okay, as an example. Okay, and then you add it up and that's what the factor total load, so this would be unfactored and factored. Okay. That becomes important because you'll see as we get to the charts or to the literature, in the tables there are some values, you'll see, I'll answer one in a minute, but there are some values for any given span that we need to look at. There are some unfactored values we need to look at, and there are some factored values we look at because we're looking at some that are driven by shear, more critical things, and others that are driving deflection and things like that. Okay. So now we'll get off track of that for a minute, just to explain a little bit what influences flow performance. Okay. I just showed one up there, joist depth. Any other things that you might call out you might think affects flow performance? Any ideas?
Bridging and strapping.
Good. Yeah.
Spans.
Span, absolutely. Yeah. Anything else? Sheeting. Exactly. Yeah. Absolutely.
Connections like screws or hangers.
Yeah, to a lesser degree, assembly could be. I'll kind of talk about that in a second. Joist spacing is another one. Okay, so the wider the on-center spacing, the more the sheeting would have a tendency to deflect between that sheeting. Okay, the thickness of the decking has an importance. Okay. The span, as you're saying, the longer the span, the more that can affect the flow performance. And again, this is